Thank you very much for giving me the opportunity to present our work in this symposium. And I will start right away with a brief presentation of our work that we have conducted in the context of indirect dark matter searches and in the context of a non-consortium publication inside CTA collaboration with the title Cherenkov Telescope Ray Prospects for Annihilating Dark Matter from Observations of Nearby Spiral Galaxies. And below you can find the list of the authors that contributed in this talk, and of course the instrument that we have selected for our searches, which is no other than the Cherenkov Telescope Ray, the upcoming gamma ray observatory that is operational at very high energies up to 100 TeVs. And as we have already discussed, CTA is actually consisted from the three different sizes of telescopes: small, medium, and large. And at the same time, it offers a full sky coverage, given that it consists of two different arrays, one in the northern and one in the southern hemisphere. And it also foresees a factor of 5 to 10 improvement in sensitivity in comparison with current IACTs, giving us the opportunity to proceed with dark matter searches with unprecedented sensitivity. And in the context of this work, we have selected as dark matter targets that are not that frequently considered before as dark matter targets in the literature, which are the M31 and M33 spiral galaxies. So we would like to see how much CTA, what is the expected sensitivity of CTA, even towards dark matter targets that they are not that close in distance, such as the galactic center, they are not that highly dark matter concentrated, etc. So first of all, I will do an introduction to the software that we have used. So when we started these studies, these searches, actually GammaBy was not selected as the main software for CT data analysis in that case. So we have selected CTools as our software, and we proceeded with simulations, given that CT is not operational yet, of course, with the exception of the first LST in the northern array. And we fixed the simulation time for both dark matter targets to 100 hours. And in the field of view, we consider, first of all, the residual cosmic ray background, as well as astrophysical background emission, which can come from point or even extended sources. So we went through the literature and we selected, first of all, 4-point sources for the case of M33, 6-point sources in the case of M31 from the latest 4th Fermi-Lat catalog, as well as an extended emission coming from the inner M31 bulge. And we proceeded with constraining the parameters of WIMP, so when considering weakly interactive massive particles as possible dark matter candidates in this case. And of course, we did not include any contribution from the annihilating dark matter to the simulated data. So for the derivation of the upper limit, the methodology that we followed was the template fitting analysis. So we constructed different templates, which are actually consisting of the J-factor values that we actually calculated by Python scripts and at the same time cross-checking them with the ClampPy software. And ClampPy gave us also the opportunity to proceed also with considering the existence of subhalos, but in this brief presentation, I am not able to present all the results, so I have excluded this part of the results. So here at the right bottom corner, you can actually find a template sample where we have the J-factor values, of course, normalized, with the peak at the center of the galaxy for the case of M31, and how the J-factor value actually decreases as we go to larger distances from the center. The counters here are illustrating just a decrease by a factor of 10 each time to the J-factor value. And the main takeaway message here is that those astrophysical sources in the background actually do not contribute, and they do not have largely to the obtained dark matter signal. So they do not affect the upper limit results that I'm going to present, and therefore we haven't included them in the paper. So first of all, before we go to the main results from dark matter, I would like just to make a small parenthesis and focus on this inner M31 bulge, which is an astrophysical emitting source, which has already been detected by Fermi-Lat. So we wanted, in the context of this paper, also to try and find out if CTA will be able to detect this source. And for that purpose, we actually, first of all, take this paper, the main results, which is actually the spectra of this inner M31, the best fit, which is a parallel with an index of minus 2.8, which is illustrated in this figure with the red dashed line. And we also interpolated the data from other surges for the case of the spectrum of M31. And we proceeded with a calculation of the upper spectral limits in the case of CTA by considering the same normalization as in the case of this parallel, and extended it to the higher energies of CTA by considering a constant index of -2 in the parallel in that case. And we found out, and this is the main result, that the simple parallel fit that we performed resulted to a parallel index value of -2.31 or harder in order such a detection to be possible with a 5 sigma significance. So this is the statistical value of 25 that we see for a parallel index of -2.31. And now I will proceed to the main results, which is the dark matter results. So those are the velocity average annihilation cross-section as a function of this energy. And from all different profiles that we found in the literature, we actually select here a benchmark profile, which is reported in the Dimaro et al. 2019 paper, and which is a Navarro-Franken-Wyatt profile for the case of the M33 galaxy at the right panel, and an Astro profile in the case of M31 galaxy at the left panel. And what you see here is actually velocity weighted average annihilation cross-section as a function of the dark matter mass for 3 different annihilation channels that are frequently considered before in the dark matter studies. And the difference that we have here is that in the case of M33, we went and calculated the maximal zenith angle. For reasonable quality observations, we found that for M33 position is offered for observations from both the southern and northern CTA side, and that's why we have doubled the number of plots in the case for M33 than in the case of M31, which is observable only from the northern CTA side. And the main conclusion is, of course, that we have higher sensitivity of CTA towards the M31 target, and the best case sensitivity scenario is obtained for the case of M31 galaxy and reaches an upper limit of 510 to the -25 centimeter cube per second for the tau-tau annihilation channel, and for a dark matter mass approximately 0.3 TeV. So this brings me to the last results that I'm going to present here, and those are connected with uncertainties, which can originate from the uncertain dark matter density distribution in the center, in the inner region of the galaxies, as well as systematic uncertainties, which are connected with the poorly knowledge of the instrument itself. So let me start first from the first one, the first results, which are connected to the uncertain dark matter density distribution profile. So from the literature, we have selected for M31 13 different dark matter density profile, while for M33 7, and we proceeded with a calculation of the uncertainty region. So we calculated upper limit results for each of those profiles, and we present here the uncertainty region, which is illustrated with a gray region here. And this means that if we consider a core or a cusp profile, so if we consider that the dark matter density distribution rises steeper or flatter towards the center, we can get a result which is actually an order of magnitude difference to the upper limits. And this is for the case of M31. This is for the case of M33. Again, 2 different plots, one for the southern and one of the northern CTA side. But we didn't stop there. We also wanted, given that we're talking about simulations, to calculate uncertainties connected to the randomization of the event data due to different realization values. And therefore, we selected 50 different realization values, and we proceeded with a calculation of the uncertainty region. So each time we're proceeding with a C-tools analysis, calculating the upper limits for different realization values. And we obtained this yellow uncertainty region, which is actually negligible in comparison with the uncertainty from the different dark matter density distribution profile. The red and magenta lines here are just the benchmark profile for the Astro profile and for the mean value inside this yellow uncertainty region. And this brings me to the last results, which are connected to the systematic uncertainty. So we proceeded with an assessment of the impact of the systematic uncertainty of instrumental origin and or related to the misidentified cosmic ray background. And we follow two different methodologies. The first one has already been proposed in the Dark Matter Galactic Center Consortium publication, Akaria et al. 2021, which is based on a modified Poissonian function. And the new one that we bring here, which we call time limiting methodology, is an alternative methodology which is based on the energy spatial binning size, for which systematic uncertainty becomes equal to the statistical uncertainty. And for that purpose, I illustrate here the main results, again, annihilation cross-section as function of the dark matter mass. With the black solid line, you can find the main results without any systematic impact, while with the red and the blue lines, you can actually find the two different methodologies. With the red, the modified likelihood Poissonian function that we're considering, and with the blue, the new time limiting methodology that we propose. And in all cases, we have a 0.1 degree spatial size and 10 and 3% energy scale. So with the dotted line, we're talking about 10% energy scale. With the dashed line, we're talking about 3% energy scale. And the main results that we obtain here is that the 10% energy scale systematic uncertainty can result even to an order of magnitude worsening of the upper limits, while we, however, explored lower levels, such as 3% or even 1% that I do not present here, to illustrate the scientific gain of the decreased level of systematic which can be achieved with the next generation instruments. And most importantly,
it's finished soon. Sorry.
This is the last slide with the conclusion. And most importantly, we were able through this new methodology to free some CTA time, which can be dedicated to searches of other instruments. So shorten the time of LSTs, make it more extended for SSTs, and we proceeded that way. So this is the last slide, which is just a summary. So we compare our results with different searches results. So with the black solid line, you can find upper limits results for the case of M31, and with the dust for the case of M33 galaxies. All the others are targeting different dark matter targets, and they're considering different instruments. And the bottom line scenario here is that CTA will be even more sensitive than Veritas, for example, towards dwarf galaxies. Of course, it appears that it will be less sensitive in comparison to HAWC, but we have to consider that we're targeting less dark matter concentrated targets at a closer distance, and at a closer distance, of course. And the last line that I want to say is that we found the search from 2018, which is dark matter surges towards the same M31 galaxy and for the same main astro profile considered by HAWC at 2018. And the main result here, which is presented with the red dashed line, is that CTA appears to be an order of magnitude when considering the same dark matter target and the same dark matter density distribution profile in comparison to HAWC. So thank you very much. That was the end of the presentation.